online faculty development program on advanced antenna design for next generation wireless communication system 5G, 6G with AI perspectives. We request all the participants to stay connected throughout the session. As we begin our session 4 of our faculty development program, we are honored to have with Dr. Yogesh Salukhe, solution consultant and tech expert of Via 3D. To formally introduce our esteemed speaker, I now invite Dr. Saurabh Gaur sir, Head of Department Electronics and Communication, MIT Ujjain. Sir, over to you.
Thank you, Dr. Pant. Good evening, everyone. Namaskar. It's my honor to introduce our distinguished speaker for today's first session, Dr. Yogesh Salukhe. Dr. Salukhe is a highly skilled solution consultant and EMAG technical expert at Via ACE 3D with over 5 years of experience in the RF engineering domain. He has cultivated deep expertise in RF design, antenna system, and electromagnetic applications. He is working in Via ACE 3D from last 3 years. Before that, he served as RF design engineer in Hyderabad and antenna electromagnetic engineer in Ahmedabad. Dr. Salukhe holds PhD in communication engineering from VNIT Nagpur, MTech in communication engineering from IITDM Kanchipuram, and BTech from MIT Aurangabad. He has published more than 17 research papers in SCI, Scopus, and international conference journals. We are truly fortunate to have him to share his insight with us today. I request you, sir, kindly address the participants. Thank you.
Yeah, hope I'm audible to you all.
Yes, sir, you are audible.
Yeah, please let me confirm for PPT. Is my screen visible to you?
Yes, sir, it's visible.
Thank you. Please confirm whether slides are properly
Yeah,
shown.
it's
Yes,
visible.
sir, visible.
Okay, thank you. Thank you so much. Yeah. So before start, I'd like to thank Mohit sir for giving this chance to discuss regarding RF and microwave and antenna related things using CST. Hopefully, some of the participants, as I can see, the title is AIML and 5G 6G communication. So today's talk, what I'm going to discuss is related to communication with RF and microwave using one electromagnetic software, which is a CST Studio Suite. So I would like to start with the introduction of where do we use antennas if you see in current world. If we talk about any industry or any areas which we can talk about, everywhere we can see antenna plays very vital role. Some of the industries has been listed here, started from automotives, aerospace or telecom industries, now into the robotics, smart city analysis, transportation and mobility and aerospace and satellite communication. So most of all industries, if you see, which they communicate with the help of the antennas. So if you talk about any industries, most of all will be preliminary requirement will be design of an antenna. So antenna plays, I can say, a very vital role to do any communication in current world. So we can start with the question means like, what are the antennas then, who needs them and all. So if you put simply an antenna which converts the guided electric energy into the radiated electric energy, where we receive the signal or transmit a signal with the help of free space communication. Here, one of the simple example is been listed out. One which is a dipole antenna, you can see on a screen, which is on the left hand side. Once you excite the dipole antenna, the electric field will travel all along the conducting part, both the dipoles, and through the free space, it will radiate it into the free space. So on the right hand side, the image illustrate which is a horn antenna. Once you can see here, the energy goes in from here. Mostly we divide the radiation pattern into the two prospects. One is the near field region and one is the far field region. And both these regions are depend on the operating frequency. Whatever antenna we are designed, it may be in gigahertz or megahertz or near field or far field communication. So depending on that, these both the regions will be defined for all types of antennas. Then if you see from where the power will go, how it will radiate at all. So there we have the input ports from where our P stimulator will be excited into the any RF component. In this case, it is a horn antenna. Some of the power will be reflected back and coming back to the same port from where we are going to excite. Some of the power will be going in with the help of whatever matching networks or the a coupling we are going to design between your connector and to the RF component, in this case, which is a horn antenna. And then there are some losses will be there due to the material losses and the mismatch losses and all. And then we get some power to be radiated into the free space, which is our required energy to do the communication. And while doing this process, some of the components are very much important, like a radiation field and the efficiency of an antenna. So both these things will be calculated during this process using a software which is a CST, which we listed. Taking one of the example, which is an antenna. If you see in the current world, antenna is backed by the multiple RF components, started from the PCBs, dividing units, amplifiers, and most important is the antenna. So what we are seeing in today. Here one the image, whatever I'm showing, which is a radiation pattern of an antenna. So once you excite, or we are going to use initiate a call also, there is antennas will be enabled, and we can see there are some electromagnetic field will be radiated from that. So this is how it looks like once you start any communication, whether you are going to navigate, whether you are going to call, or using a Bluetooth for your Wi-Fi connections, Bluetooth connections or Wi-Fi connections. So for all these process, you have to excite your antennas and it will radiate its electromagnetic energy or electromagnetic field into the free space. So during this process, talking about antenna itself, there are multiple challenges we face when we talk about as a researcher or as an industry person also. We always want whatever we are going to design, it should be fast enough when we talk about the time. We should not be late into the market for any type of antennas. Like our competitors should not come before or design or do the prototype before us or after us. There are large number of product varieties, so wherein we need very much important biggest challenges I can say, which is a re-engineering for each model. Again, unwanted interaction and interference. So this is related to the electromagnetics again fully, wherein we have seen in this example itself, which is a mobile phone, which is backed by the multiple RF units, multiple antennas, multiple PCBs, the casing of the mobile itself. So all these are the electromagnetic absorber or reflectors, I can say, which deals the effect into the electromagnetic interferences. So once you have excited an antenna, the fields will radiate. And due to the other conducting elements, that field will be coupled into that. So we need to take care of that also, which is the biggest challenge when we design any RF component into the electromagnetic field interference case. So these are the three listed challenges are here. Away from that, we have multiple issues also, which plays again a challenge role here. So I'd shown talking about antenna only. I'm limiting my communication for the mobile phone application itself. So where you can see, like once you open your mobile phone, you can see there are multiple RF components are there, or the electromagnetic field are passing through all these components. There are multiple antennas are there. If you see here, like 4G, LTE antennas. And currently we have these 5G antennas, GSM for Wi-Fi communication. We have these Wi-Fi antennas. And there are two units of 4G LTE antenna, DCS communication, which is an inverted F antenna. Then we have these 5G antennas for GPS navigation. We have these GPS antennas. All these antennas are there, which needs to be designed. And again, taking into the account of interference. If you see these cameras, all these PCBs and the battery unit also, all this plays very vital role to check the electromagnetic interference. If it is required in the cases of an array antenna, then it leads to the increment in the gain. If you talk about in communication, so gain will be increased. But if interference is unwanted, it degrades the performance of any RF component. So we need to very much smartly choose the component and its location also, where we need to place into all these casing unit itself. So you can see one of the P5 antenna, 4G LTE has been excited, but if once you have excited a particular one element, you can see there is unwanted field has been coupled onto the another antennas, and some of the fields also can be seen on the surface of the battery unit also, because this is also conductive. So all these are the points which we need to consider while designing any RF unit. So by discussing into the antenna prospect only. So this is one of the general process for designing, fabrication and measurement of your antenna unit. Always any engineer or any researcher starts his journey getting specification. So in industry, we get something like this specification, like whatever antenna we are going to design, it should not be too big, it should not be too heavy, it should not be too much expensive, using high cost dielectric materials or increasing the multi-layer aspect. Some of the times now the requirement is coming wherein we need structures to be flexible and robust. These are some of the general requirements or specification will come from the industry. But again, as a antenna engineer, preliminary what we want is the operating frequency of that device. So this specification is the very much preliminary requirement, where what is the operating frequency, how much band of operation will be required while we are designing these antennas, how many types of polarizations you need. You need a single polarized or dual polarized antenna, which type of feed network you are looking for, what is the total scan angle, considering the theta and phi or elevation or azimuth angle. So these are some of the specification we get once we need to start designing concept. Then we come into the second stage, which is a design. So once we get the specification, we can list out some of the types of antenna, like here in this case, which is a sharp fin antenna, depending on requirement, what antenna we want to design. So we can go ahead with microstrip antennas or 3D antennas like a horn or helical. So that all aspect will come at the design stage. Once we get the design, depending on the solver, which is an intermediate step of the design and the simulation, we need to select the solver. As we are discussing regarding the CST software, which is computer simulation technology electromagnetic software, there are multiple solvers are available, started from time, frequency, integral equation, and asymptotic, which are some of the general purpose solver. And all these solvers are backed by the mathematical technique, like time domain is backed by the FIT technique, which is finite integration time domain technique. Then frequency domain solver uses the FEM, finite element method technique. Integral equation uses MOM, and method of moment and MLFMM technique, multi-level far to multi-mode technique. And asymptotic solver uses SBR shooting and bouncing rate technique. So all these techniques will be available depending on our structures, which structure it is, how much big it is, how much small it is, and what are the result and outcome we are looking from that particular structure. So these all will come under the simulation stage. And once we set up the solver, we come at the result stage where we see what is the electromagnetic field performance is there. So these will come under the certification task, where we see once we have designed antenna, what is its scattering parameter, how much amount of bandwidth has been achieved, If it is a MIMO, then how much amount of coupling is there, cross coupling is there. Once we go into the 3D side, we can see its radiation pattern and polar plots, co and cross polarizations and all. And once we are okay with whatever certification or whatever specification was there, if we match that, then we go ahead with the success and reporting, wherein we have to fabricate and measure do the measurement part of that. And we cross check whatever we have simulated, whether I'm getting same result or not. So all these come under the success and reporting stage. If you are not okay with the result, again, we have to come back at the design stage and do some modification to achieve proper result. So, which is a general process of designing. But what is the solution we have? Once we talk about, I need to design an antenna, what is a solution for that? So, we have these 4 different workflow process. I'd like to discuss these 4 topics as of now, wherein we have these simulation techniques. Then we have this antenna simulation, then safety and certification, and antenna into the environment, where once we design an antenna, we used to place that antenna into the real environment. So if I design an antenna for mobile phone, you need to place that antenna inside a mobile phone and see whether whatever requirement or specification was there, whether it is matching or not. If it has been designed for aircraft application, then you need to place that antenna on an aircraft and see the electromagnetic performance. So we will discuss regarding these 4 topics in today's talk, and I'll show some of the CST models also. And meanwhile, if you have any doubts or any questions, you can raise your hand or you can ask also. Now started from simulation techniques. So there are some of the techniques are available. Those who are currently using this CST electromagnetic simulation software, they are aware about all these solvers. But again, depending on the application and electrical size, we used to divide the problem and the solver setup also. If you can see here, along x-axis, which is a bandwidth of our device, and along y-axis is the electrical size of the device. So if you are falling into this quadrant where your electrical size is very big and the bandwidth of the operation is very narrower. Application, if you talk, like same, the sharp fin antenna, which is placed on an aircraft, or antenna with the reflectors and multiple units. So all these cases will come into the asymptotic solver. So you can go ahead with this asymptotic solver. If you have an antenna whose bandwidth is quite wider and electrical size is large, then you can go ahead with time domain or TLM solver. And if your structure is highly resonating and electrical size is quite small, like narrowband antennas or anything related to that, then you can use the frequency domain solver, which is backed by the FEM technique. Again, when we talk about a solver, we have to again see which solvers are the full wave solver and what are the ray trace based solvers. So time domain, frequency, and integral are the full wave solvers, and asymptotic, which is a ray trace based solvers. Depending on the shooting and bouncing ray technique, it do the electromagnetic analysis. For most of the cases, what we are discussing for antenna, we can go ahead with this 3 technique, FIT, FEM, and MOM. And SBR, we can go ahead with the asymptotic solver. Again, here itself, 2 things I would like to again mention here is like those who are working on the circuits and multiphysics analysis, you can use this solver called as time domain, frequency, and integral. Why? Because there is very good amount of communication is there. So take an example where you need to place an antenna on an aircraft or in a car or mobile phone. So in that cases, there are multiple ways of doing simulation to that. You can export the radiation pattern as a source, or you can just take that source radiation pattern as a block into your next schematic simulation. And all these can be done it here in the circuit analysis part. So in the circuit analysis, one point I can mention here is like if you are working for lumped element analysis, or any analysis which needs your amplifiers or inductors or capacitor, you can use this circuit analysis which is available with CST to do this analysis. One more example here is like if you have designed an antenna whose input impedance is not matched. So in that case, To do the matching network, you can use this circuit analysis, and you can do the matching network analysis here in the CST also. Now going inside the antenna design, those who are beginner or for antenna designing, or those who want to design an antenna with the help of antenna makers. This antenna makers is a tool which is a synthesis tool. What it do is like you just need to do this specification. Once you got specification from anyone, or if you're a researcher, if you want to design any complex structures or antenna, this antenna makers will help you a lot. So what it asks you is like whatever application you want to design, you need to select that. Let's say I want to work on the 5G band, so you can set up that 5G band. Second task he asks is like what is the operating frequency of an antenna. You need to give that input, how much amount of bandwidth is there. Once you set up a percentage bandwidth, it will automatically calculate its minimum and maximum frequency. And some more inputs he will ask you, what dielectric material you need and all. So once you give that inputs, you will get this near about 15 to 20 different types of antenna, which give you same result, whatever inputs you have been given. So this is very smarter way of designing, wherein you can just get the structures, export into the CST, and if you want to do the optimization, you can do it in CST also. So which is a synthesis tool. So just give your inputs of operating frequency, get the 3D structures, export it to the CST, and see the performance also. This way you can do some of the antenna I have listed here. Like if you want to work in 3G PP band of operation, you have some of the different antennas. Again, if anyone wants to work in the 5G or waves or any low frequency application, you need to just set up that frequency band, and we can see some of the models will be already available over here. Like we have seen for mobile phone, which is requirement is an inverted F antenna. So that is can be very much easily exported from here. If you want to bring any CPWG antenna, you can see here there are some of the listed things are here. And away from that, which is a big library of an antenna makers, you can see once you use CST, depending on your requirement, you can set up and antennas also here. Now, once you have seen some of the types, you can compare their scattering parameter also. Okay, you can see here whatever will be the best suited for you. In some of the application, you may need a multi-band antenna. You can give that input also, that I need multiple bandwidth. And out of all these, you can do the comparative analysis also, which suits your requirement. You can export that antenna into your CST also. So this is very easiest way of designing any antenna for any multi-band or any different difficult application wise also you can set up. Now some of the antenna has been listed here as we discuss some of the types considering mobile phone itself, where there are multiple antennas which will be required. Some of the compact monopole antenna is here. Again, those who are from industry side, they will come to know that we need to do the simulation both in a single environment. If you have PCB, you can see it here, and which is connected with an antenna. So both you can do simulation. Once I have excited how much amount of power is been going in and what is the behavior of my antenna once I do the real environment simulation inside any casing or any real-time environment. So all these simulations you can do it. All types of blade antenna using F-domain solver or any time domain also you can use. Again, depends on the bandwidth. If you are designing antenna with a reflector or an antenna with a reflector which is bounded by the radome, again that is also possible. With the help of integral equation solver, you can simulate that. You can see the radiation pattern of your antennas and all. Now dividing here, considering the MIMO antennas or mutual interferences. So let's say you are working on 2 to 3 different types of antenna, and some of them are the transmitting antenna, some of them are receiving antenna. So to check the interferences, is there any violations are there or not? These again will be required for those who are working in the multiple antenna communication system, where you have multiple antenna, which is a transmitting, multiple receiving antenna. And CST will help you a lot to check the cross coupling here. Cross coupling means whether there is any interference is there or not. So here you can see like what are the antennas are communicating with that, whether it is good or not, which is required or not, whether that whatever interference is happening, it is good for you or not. So that check you can do it with the help of this interference violation matrix. Sorry. And very much easily we can, again, it's like this also gives you very one interesting analysis also. So that if there is interference is happening, what you can do is like you can just change its location. Okay, if you have placed that over here, and we see that there is interference is happening due to this 5G antenna, but which is not required. So what you can do is like we can relocate this antenna into the some other location which is best suitable for you. Again, software with the help of this visual graphics also we can check once I've excited where the field is traveling. And wherever there is a minimum electromagnetic field is there, you can place that antenna into that location also. So that type of visually cross-check things also you can do it with the help of this software. Those who are working for 5G waves antenna array prospect, that is also you can do it with the help of this CST. If you want to design a linear array with a multiple substrate or dielectric or multiple conducting layer, all these are possible. If you want to design a square array, that is also you can do it in CST. This is a design workflow. Those who are working on phased array antenna concept, where the input phase or any techniques you can use to change the or to steer the beam of your antenna. So this is one of the workflow, how it is go. Same thing I'll replicate into the CST also, so that you'll have an idea how I can design single element and convert into the array also. So if you have a single element, with the help of, you may can bring that with the help of antenna megas or can design inside a CST also. Then you can convert into the array also using this array task, which is available here in CST. If you want to do the real simulation, then you will have this housing. With the help of this housing, you can import that antenna into the housing and see. This housing is nothing but a radome in this case. Whether your electromagnetic performance is changed or not. So that is also cross-check things you can do. And once you do that, you can see how the radiation pattern of my antenna is actually scanning. So this type of simulation of antennas, antenna array, phased array antennas, that you can do it in CST. Those who want to work or they are working in TX and RX antennas, both in single so environment, that you can do it with the help of CST. There are very much good amount of coupling is there between your time domain to integral to time and coming back also. So this come under the bidirectional hybrid simulation task. With the help of that, you can have any structures like these big structures cannot be simulated using the general purpose solver. So CST is having some dedicated solver like integral equation and asymptotic solver. With the help of that, any big structures you can simulate, whether it is an antenna array which is placed on very big satellite or any pole also for your TX and RX. So all these things which we called as antenna placement scheme, you can do it in CST. Like here you can see you have this one as a TX, this one as a RX. Once you excite how much amount of power has been received at RX end, that is all you can check. How your radiation pattern is there, that is also you can check it here. Whether there is any unwanted coupling is happening or not, that can be also cross-checked with the help of port analysis here in CST. This mostly we see the S parameter, how it is behaving and all. But one point here I want to highlight is the optimization. So CST is having different optimizer, like here which is listed, which is a topology optimization. With the help of that, any structures can be optimized in such a way that you should have the proper way of analysis to that. Means like if you have a rectangular block, if you want to do any R&D into that, so that I can come up with a novel structure with the help of this topology optimization, these structures can be converted into multiple shapes, but still you will have somewhere similar result over here. So that type of structure novelty optimization, you can do it here also. So that you will have at start you'll have something like this result. You can optimize that for some different result, different models, and you can try to achieve similar result also. So this type of structure variation, you can do it with the help of this topology optimization. Again, further going there, if you want to do any bending analysis of your component, that is also possible, and you can do it here in CST. Shape optimization also you can do. So this talks about a horn antenna again. If you have designed an horn antenna and you want to bring some novelty into that, so with the help of this shape optimizer, which is available with CST, you can just modify its shape in such a way that you will have similar result. So this is also, you can do it here. Now, as we discussed regarding the environment, here the same case I'm using, which is a mobile phone, which is placed inside. We have these multiple antenna units. Here in this case, we have this array of 4 element 2 by 2 used for wave or 5G antenna. Once you extend that, you can see here how your electromagnetic field has been radiated into the free space by crossing your mobile phone casing, which is also radon in this case. And as I told you, to avoid the interference very much easily, we can see where are the less amount of electric field is traveling. And we can identify that location. You can place another component to that location, and so that your interference will be minimum. This is again for automotive industry, those who are designing there. So you'll have the antenna will be placed inside this type of casing, and you want to understand, or we need to do the study once I place this car model in front of my antenna, how my electromagnetic performance is being there. So that can be done here. One of the frequency band has been listed, which is 77 gigahertz for automotive radar application. If you are working for aerospace and defense industries, that simulation also you can do. CST gives you very wide variety of feasibility thing, so that any small structures can be simulated into the big environment of like aircraft. You can see in this case helicopter. So you can place your antenna here, you can say, and these big structures can be imported, and then you can see once I've imported this, how my antenna performance is changed. So that real-time environment simulation also you can do it here. Again, while doing this process, how my scattering parameter is changed, or the radiation pattern, cross-section view of that at azimuth and elevation plane, how it is behaving. So that is also we can cross-check here. Again, these are some of the things which has been necessary for the industry person to do the coupling metric analysis, the RF system analysis, and the interference matrix analysis. All these we can do it here. This coupling matrix is for how much amount of coupling is been there when you have multiple RF components. RF system simulations, when you have multiple antennas, how that antennas are behaving or communicating. So that is also you can do it here. And this talks about its performance, whether interference is there or not. So that matrix check, we can do it here. In the safety case, again, at the end, those who are working for biomedical application, if you have antenna which has been designed at so and so frequency, once you kept inside a mobile phone and near to the head using a phantoms or any voxel data, we can see how it is behaving. Once you excite, you can see how electromagnetic field has been traveling. And mostly we do SAR simulation, which is specific absorption rate. Here you can see at your resonating band how much amount of SAR is there. We have some standard limitation value for that. So to pass that certification, we should have that SAR value to be minimum. As we can see in our mobile also, all mobile will have its SAR value. Around 1.6 watt per kg is the threshold value. If you have designed an antenna which is less than that value for mobile phone, it has been certified that you can use that mobile, or you can use that antenna inside the mobile phone. Here one more point is like CST is having very wide variety of library of this phantom. So you can place your antenna inside any phantom which is required for a human body, or any different phantom of an animals are also available. So you can place that and you can see whether it is useful for you or not. This is for which are for station towers. those workers who are working into the high powers scheme, we need to do that analysis also, whether this power, whatever will be radiated due to this station or tower, which is affecting or not. So that analysis also you can do it here in CST. Whether you can see that red part indicates the high intensity field. Okay, so once you excite how much amount of field has been traveled, you can do the SR analysis on human body and you can check whether it is hazardous for us or not. Here, the human body exposure has been listed like SAR analysis or wearable devices. We have these different phantoms are available. So if you are designing, working for ear aids type of analysis or mobile phone, you need to have different ear locations or the ear shapes will be required. So that is also you can, it is available with the CST. If you are working inside the body where implantable things like the stand which we going to use inside a leg or any bone type of this. So all these phantoms are available. Movement based things is also there, like heart pumping and all. So that you can cross check and you can use this phantom. If you're working for automotive industries where we have these different phantoms, if you're driving, how your location or how your position will be there and how much amount of electromagnetic field will be affecting your body and all. So that is also all these analysis you can do it in CST Studio Suite. Again, antennas is not just for electromagnetic analysis. Away from that, you can have the whether it is performance is there or not once it is fallen from a particular height. So that analysis also you can do it with the help of Abacus and CST collaboratively. Which material I need to use and also for that purpose you can have this metal frame analysis also. For car and all, again, all these things are there. So once you have designed an antenna for automotive radar application, you can place that antenna inside this car and you can see that behavior also. So end-to-end solution can be analyzed with the help of CST, whether it is for automotive or for mobile phone, for telecom industries or aerospace and defense. For everywhere we can see the effect of that. And with that, I would like to focus those who are working preliminary or only for antennas or antenna array concept. So for those, we can see it here. I have one is like how real environment simulations are possible. It has been listed out here. If you are designing any array, single element also, and you want to convert that into the array with the help of array task, how that can be converted. And if you're working for radom also, means like if you have array antenna here, you can see which is bounded inside a radom, how these analysis can be done. That has been shown here. So you can see it here. You have this antenna with your casings and multiple these things. So different location of an array antenna also you can place it here. Not a regular 2x2. You have multi-layer schemes. On tops you have some antennas. On bottom side you have some antennas. So all these facilities also are available with the help of CST. You can see here how this array has been created. I'll show you in CST also how this can be created. But a small video of this has been shown here, where one more task here is like you have two different excitations also. You can do the grouping of that also. Those who are available on the front side or on the bottom side, you can excite that both different excitation can be used here. So that is shown in this video. And at the end, here I'd like to, so this is what the real environment simulation which has been done into the system simulation, where you have an antenna which is over here, and you have some excitation or power divider network or the coupling matrix, and you have this radom which have been placed. So all these you can simulate inside a single environment, inside the system simulation. Okay, these are not away from CST, it is inside CST only, whatever we are doing right now. And there is one hybrid task which are available here. With the help of that, all these can be assembled inside a single environment. and you can set up your resonating frequency, which type of excitation you want to give, that is also you can set up here. And at the end, you can see this is your casing, these are your antenna units, and power dividing networks or excitation units also can be seen. And all these are available inside a single environment. You can see all these layers from where your excitation or electromagnetic field will come or power will come to excite your this thing. You have multiple excitation sources. All these far fields can be seen with the help of different excitation. Again, combined result. Once I excite all the ports at same time, how the performance of my total structure is there. That is being shown here, like combined analysis of all these array units. So different phase shift, if you want to give, that is also can see. Now, how this array task can be given, I'll show you here. So in the schematic, we have this task. As far as I know, single elements are very easy task. Anyone very much easily can be created and designed. But once we go into the array task, those who are working for MIMO or for array only, they have these tasks which are available. And again, it is not limited to this. There are multiple shapes are available. If you want to go with the custom base, that is also you can do. You need array in the diamond shape or hexagon or rectagon. So depending on these selections, this array will be created. Again, there are two things are listed here, which is set active and set passive. So once you have created an array from single element, if you want to excite all elements, you can set all as active. Again, these are for those who want to need a beam to be steered in a particular direction. So for those, these are very much important. And for outside, I don't want to excite that element. So you can set that as a set passive, means there will not be any excitation will be assigned to this port. So these also very much important for beam bending concept. We can use some different excitation techniques also, like here in this case, a Taylor excitation has been used, but again, depending on application, we can set up this one. Yeah, excitation, you can export from the outside also. If you want to excite all these elements with different phase shift or different amplitude of that. So that is also from external also we can assign that by importing that .tsv file. And how that array can be created, once you have designed a single element, you can go ahead with this array task. If you want to do a unit cell analysis simulation, if you have limited hardware, then you can go ahead with this, create a unit cell simulation project. If you have good amount of hardware, you can go ahead with this array simulation, full wave array simulation task also. In both process I have listed here. If you want to go ahead with unit cell analysis with different phase of excitation, that is also you can do it here with for theta and for phi. These are mostly required those who are working for meta surfaces or for frequency selective surfaces. For those unit cell analysis will be required, so that they can again use the same process over here, whatever it is listed. And once you excite, you can see how your H-plane field wedge field traveling is there at different theta. Let's say you have a theta scan at 0 degree, then you can see this. At 30, how amount of electric field is traveled or radiated field is there. So that is visually you can see it here. If you want array in this fashion, through antenna megas also you can bring that. Okay, so that is one of the advantage here. With the help of those who want to work for phased array antenna, total phased array antenna module also you can bring from the antenna mega. So we have this array task. If you want array to be linear or rectangular or circular or a triangular, this one. So depending on your requirement, you can select this synthesis process and you can bring inside a CST also. Okay, how all this behavior of array is been behaving, that is also you can see it here. So to bring novelty into the array structures, we can have something like Taylor excitation or sunflower base structures are also very much people are going for, or else combine of both using sunflower and Taylor excitation, how my behavior or how my radiation pattern is there. So that is also you can cross check here at 0 from 180 to plus 180, how my field is being traveled. For finite array of excitation, you can see how we can create it here. Once we have created an array from a single element, we have this excitation list. To do the phased array, we have two ways. One is the amplitude variation, where we can change the amplitude of all individual elements. If not, then with the help of phase shift also, we can give some degree phase shift between all these excitation ports. And we can see beam steering also. Like here, you can see how the beam is steering. It is due to the amplitude or phase shift also. And here you can do some theta variation to change the beam also. But if you want, I need beam to be steered at a particular angle. By changing this theta value, we can steer a beam in a particular one direction also. And at the end, we can see individual excitation result also. We can see if you want to see how my, once I excite my 8 port, how antenna has been behaving. If you want to see element, all these individual also we can see, and combined also we can see at the end. Once I excite all elements at same time, how the total radiation pattern is there. So that is also we can do it. Zonal simulation is also currently people are doing for different application. So if you have array of antenna, you can excite the zonal wise also. Uh, I will not invest my time here. Yeah, those who are working for sub-array simulation, as we have seen how to set up things. But for circular polarized antenna, with the help of excitation and phase shift also, we can generate the CP antenna, circular polarized radiation pattern also can be generated. So how that can be generated using any standalone element also that can be seen here. So we have this different rotation or excitation of the phase. We can do it here with 90-degree out of phase. We can place these elements, and with the help of that, we can generate that field also. Those who are working for antenna placement and for defense application, for those, this is very much important. But again, investing time on this, I'll directly go into the CST to understand how the GUI of CST is there and all. But yeah, come here for those who are working for antenna placement. For those, you can see it here. For you need to place a system of a aircraft or any car model or mobile phone model, and one by one you can import all different antennas into this system simulation itself. By using anchor point, you can do the placement of that antenna also. Okay. And once you have placed, you can see how your antenna is there. Hopefully these informations are aware about you, just like how S parameter and radiation pattern is there. Do you have any doubt till this point? Any questions? Hello.
Hello.
Yeah.
Sir,
Yes.
can you hear me?
Yes, I can hear you.
Sir, good evening.
Yeah, good evening. Yes.
Sir, actually, I want to ask that if I have designed a planar surface and then
Okay.
I have to wrap it around a cloth,
Okay.
then how to do this in CST?
Okay.
I want to check the conformability of any design.
Understood. Yes. Hopefully my screen is visible to you.
Yes, sir. Yes, sir.
This is the CST. Once you open a CST, yeah, I'll answer your question and then I'll go into the GUI part of that also. So
Yes.
you can bound your PCB into multiple ways also. Okay. How? Here there is one operation called bend tool is there. Okay. So any one of these you can use depending on your application. So if you want to, yeah,
I
yes,
have used this cylindrical band,
yeah, correct.
but in this cylindrical band,
Mm,
we have to select a radius.
correct.
What that radius means?
That radius means you will have, if you have straight this surface, you can see it here, which is a straight line. And if you want to bound this, then how much amount of radius you need? Okay, that is where it is asking. So you can see it is a half circle means he have given this half as a radius to that. So that radius you can give. But if you want to bend along a particular shape, you can use this bend layer stack up. That way you can do that.
Okay.
So
Okay, sir.
that if you have a cylinder, on top of that, if you have microchip structures, and if you want to bend that, you can use this bend layered architecture setup. So everything will be bended around that.
Okay, sir. And sir, one more question.
Yeah, yes.
Sir, if I have designed a unit cell and
Okay.
then I want to do the same thing for this conformability test, how to do
Yes.
that for this 2x2 or a 3x3 array?
Means how to do bending you are saying, or how to do the analysis?
Yes, sir. Both the things. First, I have a unit
Analysis, sir.
cell.
Analysis.
Hello.
Yeah, yes.
So can you hear me?
Yes, I can hear you.
Sir. Just I have designed a unit cell, and now I
Okay.
want to make it 3x3 and want
Okay.
the same thing as a conformal, and then I want to analyze that.
Yeah, you can bend it, right? In the unit cell analysis also you can bend that. But again, if you are working on FSS part of it, frequency selective surfaces,
Yes, sir.
then in that case, you cannot bend it directly. When I say bend directly means you can bend as a visually, but whenever you are working on a particular shape structure, in that case, you have, once it is looking from the front, once it is bended, your shape will change. Okay.
Yeah.
Yeah. So nominally, it's like, again, it is beyond a topic what we have listed today, but I'll let you know main thing here. When we do FSS unit cell analysis, if you have simple structures,
Yes, sir.
let's say like a rectangular block, straight away we can do this
Yes.
analysis using this. But once you bend this, then we have to see its nearby components also. Okay, if you have a 2x2 array of these,
Mm-hmm.
okay, once you have bended, you need to bring your structure, nearby structures also into the picture.
Yeah.
So your unit cell cannot be a rectangular, this one. You can use rectangular unit cell at something like these also. I'm unable to plot it properly, but something like this, once you do the bending, you need to analyze which is the common part of that, like looking like repeating after some wavelength or nearby component. Are you able to understood?
Sorry, sir. I really don't get it.
Okay. We will connect again later if you want.
Sir, can
But
I have
again,
your
what?
mail ID so that
Yeah,
we
yeah.
can connect?
I'll put in the chat so that you
Okay,
can
sir.
have
Yes.
this one.
Yes. Thank you, sir.
Yes, yes. But if it is a normal bend, you can just bend it for FSS also or for anything. But again, if you are going in depth of FSS analysis, once you bend, you need to cross check. Uh, sorry. Once you have bended, you need to cross check how the bend is there. Once we have bended, unit cell is similar, then no issue. If it is not, then you have to do this modification change.
Okay, sir. So I will send my design as well as the questions related to it.
Sure,
And
sure, sure. I have listed.
whenever you get the time, please answer, sir.
Sure, sure. Yes, yes.
Okay. Thank you, sir.
Any other
Yeah.
queries?
Thank you.
Sir, yes, sir.
Yeah, yes,
Good
please.
evening, sir.
Yeah, good
Sir,
evening.
in CST, equivalent circuit is possible, sir. For
Which
our
one in
design,
CST?
equivalent circuit.
See, I know means like what you want. Directly equivalent circuit cannot be created with the help of CST. Okay.
Oh, for the designed antenna, you will not create the equivalent
We
circuit.
cannot create directly. Yeah. We can simulate
Oh,
equivalent circuit in CST, but we cannot create it directly. We have the
okay,
circuit
okay.
components here in CST, which is the inductors, capacitor, and your resistor. All these components are there, but how the behavior is there, that cannot be identified directly with the help of CST.
Okay. So
Okay.
the from the lumped components option, we connect the circuits.
Yes, we can create. Yes.
Okay. Sir, it's
Okay.
like
So
space, right?
yeah, P-space model also we can import in CST.
Okay,
Uh,
okay, okay.
it is not limited to anything. Okay, all types of data importing things you can do it in CST. Here you can
Okay,
see like spice models and all these data inputting thing is there. Uh,
okay,
I understood like you want to do this equivalent circuit analysis directly, uh, but uh, uh, but we need to identify what are the components will be required. Uh, Two part
okay.
here I can tell you. Once you compare with other tools, we have this tuner. Okay,
Ah,
with the help of this tuner, very much easily you can move your result from left to right, lower to higher frequencies and all.
okay.
Okay,
Okay, sir, I have
and
another doubt. Uh,
and we have this optimizer also. With that, I'll just as I told you, there are multiple algorithms are available. Okay, so you can use this algorithm to optimize your equivalent circuit model also. Okay, so that gives you good
okay.
feature. Yeah, please ask. Hello.
Okay, sir. Sir, I have another doubt.
Hmm.
Sir, what is the difference between the waveguide port and discrete port, sir?
Okay. Waveguide port is for the electromagnetic analysis. Okay. And
Okay,
port is where, or I can say electromagnetic analysis. And here for discrete is like those who want to identify voltages and current. Okay. For those, you can go ahead with the discrete port. But again,
o-
one more add-on point here is like if you have microstrip structures, it is very much easy. We can assign the waveguide port. But there are some structures where we cannot go ahead with these waveguide ports. On those cases, we can go ahead with the discrete element excitation also. You have an
okay.
antenna whose input impedance is not 50 ohm, but you need to change its impedance. For those concept also, you can go ahead with the discrete element excitation.
Oh, impedance also changed by the discrete edge
Yeah,
port.
yes. You cannot do it with waveguide ports. You have to use the discrete element.
Okay. Sir, in the both mode, impedance changes.
Yeah, here you can change with the help of
O-
discrete element.
okay, sir.
Okay, yeah, thanks.
Sir, in both the port, the
Mhm.
S1 result is very why, sir?
Which one?
S11
Uh,
return loss value is varied in two ports, waveguide and discrete port. Why, sir, this variation?
See, as I told you, this is dedicated excitation for electromagnetic analysis things. Discrete
Okay,
element is there for voltage and current. But again, going in depth, your result should not vary. Okay, if you excite with these and these, your result should not vary. Result may
okay.
vary because of some errors, I can say. Like there are multiple things to discuss. Once you accept a discrete port, you should have proper meshing of that element also. For waveguide, it will be there, but again, once you go ahead with discrete port, we have to see how you are exciting and all. If you just connect a port, I recommend to go ahead with this like this way. Okay, select the edge and then
Yes,
use the
sir.
discrete port. If you go ahead with the points, properly you have to select that point. Okay.
Okay, sir. Thank you, sir.
Yeah. Yes. Thanks. Anything else doubt? Any query?
Good evening, sir.
Yeah. Yes.
Sir, my question is placement of antenna in 3D images regarding that. So the images, 3D images inbuilt in CSG, or we have to downloaded and uploaded to the CSG.
No, 3D model, when we say like antenna placement, is like antenna placed on a mobile phone or antenna placed on a car or something like
Yes,
that is
sir.
there. So if you want to input on a car, then we have to create a car model. If not, then we can have this importing facility which are there with the help of any this because this car and all cannot be created in CST. It is a mechanical component. So these things can be imported through this import and export things. Okay. So we can do this from here.
Okay, sir. We have to download and import it here.
Yeah. Yes.
Okay, sir. Thank you. Thank you. Sir.
Yeah. Thank you.
Can I ask something, sir?
Yeah. Please. Yes.
Sir, actually, I want to know about that. I'm not using CST for designing software. At the time of my MTech, I'm designing a microstrip patch antenna. And I find out some better result as compared to my literature review. So, what about you say that if you are using HFSS also, so can you tell me if CST is better than HFSS or and it impact on the result? What's the impact on the result of HFSS as well as CST, sir?
Okay. Okay. See, we cannot say means like which is better and all, but we can compare the capability. When we see a CST, it is having wide capability where we have this time domain frequency again and all. What advantage we have is like this solver. So if you have big structures, very much easily you can simulate with the help of CST. Accuracy will be there because all these are backed by the mathematical technique of FEM and FIT. If you talk about any software that is being simulated with the help of the techniques which are available over here. But we have these multiple techniques with the help of that, or you can do all types of analysis in CST. You don't need to go here and there. If you want to do the circuit analysis, you can just click on the schematic and you can create any schematic analysis also. Okay, what accuracy we have again is like again depending on the solver, but we found that there are many researchers and many industry persons are there. They are getting good amount of accuracy when they are using CST. Again, it is not comparing when we do the accuracy analysis.
Hello. Actually, first I see CST and both are looking same. The command window of CST and HFSS both are looking same. But thank you for giving me such review that the tools which more tools are available in CST.
Yeah, thank you. Yes.
Hello. Hello.
Yeah. Yes. Yes.
Hello. Good evening, sir.
Yes, sir. Good evening. Yes, please.
Sir, I have one question regarding unique terahertz frequency. Suppose how
Okay.
to give the gate voltage VG
How to give
in
the
graphene. Suppose we are gate voltage VG when we
gate
are
voltage?
designing any terahertz antenna using graphene.
Mm-hmm.
And then, sir, how to give the gate voltage, yeah, bias voltage or Fermi voltage, we can say.
Okay. Okay. Okay.
How to
Okay.
provide.
As understood. Yeah. So someone from you only what we discuss is like discrete port excitation. Here you can use that discrete excitation source. So let's say you want to give that biasing voltage between these two ports. Okay.
Yeah.
You can just create here a discrete port and you can come
Okay.
here, which is a voltage. Yeah. Yes. Here, which is a voltage. Whatever
Okay.
voltage you want to give, that you can give it here. Let's say 1 volt or 0.7 or 20 or 5. Whatever voltage you want to give, you can give it from here.
Okay.
One more point here is like you can do here as a S parameter here to assign a port, which is number as a 17. You click on OK. And come here in the schematic. Wherever 17 port is there, you can assign this excitation over here. Again, this is not it's like straight away go. Here you have to use some task to do the simulation, new task, where you can assign that as a transient analysis or only for S parameter. You can click on that. You can go to the here, and if you give any constant value, that is also you can give it here. So this way also you can do. Again, this is not a straightaway way, but multiple ways are there. But this is easiest I can recommend over here by
But
directly
sir,
assigning.
we can simulate in graphene. Then we can provide the two ports just like a discrete and the wave port.
Yes, yes.
Actually, we are providing the discrete port for the VG. It means gate voltage. Then we will
Okay.
excitation. Then other we
Now,
can
once you
also provide the
use the
waveform port.
waveguide port, yeah. Once you use the
Yes.
waveguide port, it is exciting 1 watt of power. Okay.
Yes.
Uh, you don't have any feasibility to extend that. To extend that, again, we have to use this task, and you need to do the scaling of that, wherein your input watt power will be scaled to some other. If you want to give 15 volt or anything related to that, doing RMS calculation. So then you have to do the scaling. But here, with the help of this discrete element, whatever voltage you want to give, straight away you can assign it. Okay.
Okay. Sir, when we are designing the matter surface or unit cell, normally we are using the frequency type excited simulation setup. Then
Correct.
can I use for the time domain analysis? Most
No.
of time we are using the
Uh,
frequency domain.
yes. When you go, this unit cell analysis is available with the frequency domain only. If you are going with the time domain, then you need to create a full array and then excite with the help of plane wave. Then in that case, you can use this uh, time domain analysis. You have to use this plane wave. Can you see here?
Yes, sir.
You have to excite from this, then only you can go with the time domain.
Okay.
Because for
If we
unit cell
build
analysis, you need setup. You need this setup. Yeah. Yes, tell
unit
me.
cell. Okay,
Yes.
sir. Then when we are simulating any unit, then one is just like we are drawing the reflection phase for TE and TM polarization. Then how to
Okay.
give the T and TM polarization for reflection phase? Suppose we
E
have
and TM.
a TE and TM polarization. Reflection phase for TE and TM wave polarization. Boundary. How to do TE and TM?
What you want to give?
T and TM polarization.
See, the T and TM will be assigned, right? You no need to manually assign it. Once you excite using any flunked port or waveguide, flunked port or in unit cell analysis, once you excite, it will excite both the waves at same time, TE and TM, because both are perpendicular. So if you see
Yes, sir.
under the 2D plots, you can see the TE wave something like in this direction and TM will be perpendicular. So manually, you don't need to do anything. If you want to do any theta inclination, once I've excited, I need excitation to be at some different angle so that you can do it from here. So if you can, if my screen is properly visible to you, this arrow is what the
Yes, sir.
excitation of this angle is there. If you want to do some bending of that, I want excitation to be at 30-degree inclined, then you can do by this way. Hopefully this is
And sir,
visible
theta,
properly.
theta indicating incidence angle or polarization angle. And
No, this is incident only. Na? Polarization means like once it is reflected, then only we can see the reflected things. This is excitation, what I'm going to excite to my free this any structure.
okay,
Yeah.
okay,
If you
okay,
have any doubt, we can discuss again. Means like again, it is limited to some of the questions.
okay, sir.
Yeah.
Thank
Yes.
you so much.
No issue. So those who are new or those who are coming first time for CST, this is how
Thank,
the Hello.
One more
Yeah.
question, sir. General question actually.
Yeah. Yes.
Regarding China, now they are introducing the 10G actually. 10G. But India, when can go to reach that level, sir? Actually.
10G.
Yes, yes, yes.
Okay.
We are going only 4G, 5G only. We are getting it in India. So, what is the any structure is there? We want to reach the 10G.
Oh, that answer I don't have, but again,
That's a common. That's a general question. I'm not asking any
yeah, yeah,
regarding
yes,
that.
yes, understood,
But
understood.
really, but when we can develop? But people are saying India may develop, but when able to develop? Only speaking, huh? General question. You don't think about your negativity actually. Positively, I'm asking.
Yeah, yeah. We have to develop. As we are a research scholar, we should work on the whatever
Focus.
people are working. We are working on the 5G, then we can go ahead with the 6G, 7G, 8G, whatever you are saying. It is up to our hand. If we are working on the
Nice,
lower,
nice. Because correct, correct. You are correct. We are a technologically resource person for us. We want
yes,
to create among the students community accordingly.
yes, yeah.
Thank you, sir. Thank you very much.
Yeah. And some of you are working in the graphene, which is again equivalent to what other countries are working in terahertz frequency range. But yeah, uh, going in there, I would like to introduce this also, which talks about like here, these are the studio suite. As I'm talking, CST is very wide software for electromagnetic analysis. It is not limited for antennas or circuits. You can do the radar, biomedicals, and all. These periodic structures will come for your FSS and all. Those who are working for EMI, EMC, PCBs, and multiple casing units, for those, hello, yeah. So for as of now, we can limit this, but if those who are working for EMI, EMC simulations for radiated emission conducted, all these you can do it with the help of this CST. But you can go ahead with the antenna concept also as of now. You can limit that. Once you open, this is how its environment will look like. And we have this modeling tab. With the help of that, any complex structures or geometry can be designed. If you want to import any geometry inside a CST, that is also you can import. If you're working in any software like AWR, ADS, or any one of these software, straight away that file also can be imported in CST. If not, then step and OGB and all these features are there. That is also we can import from there. Again, we have these simulations, post-processing things, and yeah, these are multiple solvers are there. Yeah, those who are working in biomedical application, for those you can import this voxel data from here. I can list it out here. Any shapes and all can be imported. If you want to import any different animals also, that is also you can do it with the help of this CST. And different phantom shapes are there for children's and babies and all. So all these you can import in CST and you can see how its behavior is there on your human bodies and all. For those, yeah. For mobile phone, you can see as we started our discussion of today with mobile phone, you can see it here, which is a mobile phone casing model. Here we have this array antennas, we have this inverted FP5 antennas, and these array units and all. So all these are there. Cumulatively, you can simulate that and you can see the behavior of that. I have one small demo of antennas, which is a single element resonating at 4.9 gigahertz. If you are expert in electromagnetics, this is one of the moderate or basic structure I can see. But what I'm showing to you here is like how you can see as parameter, how to see electromagnetic fields, how it is traveling. We have multiple views because here we cannot see how my electromagnetic field is traveling. Okay, so we have this counter plot. With the help of that, very much easily we can see, we can do the animation of that and we can see how it is there. To students, if you, because this is an imaginary field, we can just see like electromagnetic field is traveling. But visually we cannot see, but with the help of software, we can see like our electromagnetic fields. Once we do E simulation, electric field is maximum always along the width of the patch. So by visually we can cross check here. And for magnetic field, we can see like it is maximum along the length of the patch. So that visually we can do these cross-check things and all. For radiation pattern, we can see if you want to see the structures. Transparency, we can do, let's say, far field transparency, and you can see how my radiation antenna has been radiating. And polar plots, which are mostly we see how my polar plot is there at two different phi cuts at 0 and at 90. And all these things can be seen here. One more point here I would like to say what we discussed in the presentation, which is the array task. Once we have designed a single element from here, with a single clicks, you can create single element into the array also. Right now it is a microstrip field, so it is quite difficult, but still I'll show you. Let's say I want to work on octagon shape, or yeah, let's say octagon shape with elements of 5, or let's say 4 only. Click on OK. Once we click on OK, in the schematic, we can see this as whatever we have discussed for the unit cell analysis or for full wave analysis, both can be seen here. Just cancel as well. Let's say full wave analysis. You can see, just click on OK. It will ask us what is the operating frequency of that. Let's say, yeah, 4.9 only. So here new window will be pop up. Okay, as it is microstrip, this should not be done. This is mostly for coaxial feed antenna. So you can see from a single click we have created from single element to the array of that. So that is also is possible, and we can do it with the help of CST. Those who are working on phased array antenna, you can have this list here. Once we go into the excitation, we can have multiple things here. So if you want to do the phased array antenna by changing the amplitude, we can put some parameters here. If you want to go ahead with the phase shift, we can add that phase shift degree values over here, or parameter also we can do here. So very much easily this tool gives you that guidance how to go ahead with any complex structures or array creation from a single element also. Okay. Phantom, I'll just check if I have anything that, yeah. Yeah, one simulation is going on in my system parallelly, so it is taking time to load the model. But yeah, what I'm trying to show here is like how you can import your antenna with a phantom in CST. So yeah, so if you have designed an antenna for mobile phone application, then you can place that antenna nearby head, and you can simulate and see once I excite my antenna, how much amount of electromagnetic field interference is happening to my head and all. You can cross check, or you can do that SAR analysis also here. Again, for SAR, you can do both simulation, which is electromagnetics, and thermal simulations also using same CST inside CST only. So we can have this head, you can see. You have these mobile phones which are placed over here. Okay, same models I have imported whatever I've shown. This is your screen. This is your backside casing, and your all antennas can be seen here. And you can place all these in an exact location, and you can simulate that using any excitation we can use and do the simulation. And we see how electromagnetic field is coming on the surface of head, whether any temperature has been generated, if it is generated, how much amount of temperature has been generated. So all these analysis we can do it here. Again, as I told you, it is not limited for this. We can import multiple voxel data also or phantoms also in CST. We have wide variety of library which are available, and with the help of that we can see. We can just divide this problem into the meshing also, as you know. We can check mesh also here. Okay, yeah, that's it from my side. Again, it's like we have multiple things to discuss here, but as we have limited time, I will limit myself right now over here. If you have any doubts further, we can discuss now for some 5-7 minutes. Yeah, yes.
Any queries from the participant sides?
Hello.
Yeah, yes, yes.
Sir, these features are available in CST 2024 or 25 only?
Right now, yeah, right now, whatever I shown, it is on in 2025. But yes, this all features, whatever I have discussed, it is available in 2024 also.
24 also it is available, sir?
Yes, yes.
Okay, sir. Okay.
Any queries? Yogesh sir,
Yes, sir. Yeah.
while calculating SAR at millimeter wave frequency in
Mhm.
CST, why the software takes so much time to simulate?
In which frequency? In terahertz you are working
In
or at
millimeter wave, sir, millimeter wave.
Yeah.
28 gigahertz.
20 gigahertz? Yeah. See, SCR will be calculated for both. One is electromagnetic also, and it has some part of thermal generation also.
Yeah.
But as you are working for 20 gigahertz, your mesh of your structures will become very small
Right.
because of the operating frequency. So, means like again, how much time it is taking, we also need to see or cross check. But it may be, if it is taking good amount of time, it may be due to the meshing concept also. If not, then if we have multiple things into that antenna also, if you have only single element, then it should not take. How much amount of gram we are putting. Once we simulate SAR, it will ask us how much amount of weight you want to simulate, 10 gram, 1 gram, or any custom based things. If it is more, then also it will take some more time for the simulation.
Thank you, sir.
Yes.
Dinesh Kumar, sir, any query? You raise your hand.
Ask you, sir, previously.
Okay, sir. Thank you.
Thank you so much, sir.
Thank you.
Thank you, Dr. Yogesh
Dr.
Salukit.
Yogesh Salukit.
On the behalf
On
of
the
the
behalf of the
participants
participants
and from
and
MIT
from
Group of
MIT Group of
Institute,
Institute,
I extend
I
my
extend my
heartfelt
heartfelt
gratitude to
gratitude
Dr.
to
Yogesh
Dr.
Salukit,
Yogesh
sir,
Salukit, sir,
for delivering
for
such an
delivering such an
insightful session.
insightful session.
You have
You have
explained in
explained
detail
in
about
detail
4G
about
and 5G
4G and
antenna
5G antenna
and
and
CST
CST
software.
software.
Thank you
Thank you
once again
once
for your
again for
valuable
your
time
valuable time
and
and
contribution to this
contribution to
FDP,
this
sir.
FDP, sir.
Thank you very much,
Thank you
sir.
very much, sir.
Thank you,
Thank you,
everyone, for the
everyone,
joining.
for joining.
Yeah.
Yeah.
Our next speaker will join us shortly. Ah. Am I audible?
Yes,
Wait, sir.
Okay, sir.
I'm available.
Okay. Moving ahead to our FDP program, I welcome our next speaker, Dr. Ramkrishna Joshi, sir, and I formally invited Dr. Rashmi Pant, Assistant Professor, ECE Department, to formally welcome and introduce our second speaker.
good evening, everyone. To all the respected faculty members, participants, research scholars, and our distinguished speaker. I hope you all are doing well and are as extended as I am for today's session. It is my privilege to introduce our esteemed speaker, Dr. Ramakrishna Joshi, sir. He earned his PhD in Electronics and Communication Engineering from Vishwesvaraya Technological University, Karnataka. He has been serving as associate professor at KLE Technology University, where he is actively involved in research and teaching on 4G and 5G communication systems, algorithm development, and collaborative industry projects. Alongside his academic contribution, Dr. Ramakrishna has rich industry experience as a technical consultant at DTRI Mysuru and previously at Suskin Technology, Semikesha Semiconductors, Carmel Software Solution, and Hegel Technologies. He has worked extensively on 5G physical layer design, system level architecture, and industry grade algorithm development, with collaboration include global leaders such as NVIDIA. Dr. Ramakrishna has published more than 30 research papers in reputed journals and conferences and holds patents in healthcare and IoT technologies. With his unique blend of academic depth and his industrial expertise, he is a true bridge between research and practice. Let us extend a warm welcome to him. Without further ado, I now invite Dr. Ramakrishna Joshi sir to kindly take over the session and share his insight with us. Over to you, sir.
Thank you, Rashmi madam. Thank you, Mohit sir. Thanks to the management of MIT Ujjain for giving me this opportunity to speak on the topic of interest, that is 5G to 6G evolution. Thanks for that. I hope this session would be interesting for everyone. With your permission, I would like to switch off my mic if it is okay. Sorry, the camera. Is it okay, ma?
Yes, sir. Yes, sir. You
Okay.
can.
Okay. So I hope my slides are visible.
Yes, sir. Yes, we do.
So thank you once again. So the topic that I'm going to handle today is on the 6G vision from connected everything to intelligent everything. You have been hearing Dr. Yogesh to the last 1.5 hours. Probably he might be speaking something on the antenna, which is going to be a front end part of your system. So I'll be taking the journey from the front end to the back end. So actually the opposite way we are moving today. I hope this would be an interesting one for all of us. So a few hands-on sessions also I planned, wherein we'll be looking into some codes also over there. So to start with, the 5G part, what 5G already, all of you know that, already you've been hearing since almost a decade or so, what about all 5G is all about. So when we talk about 5G, we can say that we have been moving from the 4G to 5G, and we say that we are going to have a connected everything environment over there. Connected environment, what I actually mean is we are going to bring the humans, machines, and devices into one network ecosystem. So this has been possible with three major KPIs that are going to be there in the 5G environment. That is the EMBB, which is going to be called as enhanced mobile broadband. Then we are going to have a URLLC, that is the
the mission critical services that are under the URLC, that is ultra reliable low latency communication, and also the massive machine type communication, what we call as the MMTC over there. So this is one of the platforms where we are set such that we are going to have a connecting everything that is going to be there. And as of now, the things that are moving has moved since release 15 from 3GPP that we have seen, which is the base release for the 5G ecosystem that we have seen in the 3GPP. So it has majorly governed, or we have got a major architecture which are going to be the standalone or not standalone, basically catering the EMBB services over there majority wise. So slowly we have moved towards some applications which are going to be latency related critical applications and more reliable applications which we have thought about, which are going to fall under the category of URLLC, and a large scale integration of the sensors which are going to be there in the falling under the category of the MMTC is going to be there in the scenarios. So millions of lakhs of sensors are going to be integrated, and those data are going to be aggregated and all. So the time has evolved, and we have moved from release 15 to almost release 20 as of now, wherein we are in a verge of giving us from 5G to 5G plus we have been talking about, or the 5G beyond. Few terminologies talk about that, and then we have been talking about 6G evolution also in the recent past over there. So if we understand this, like what has changed actually over there is going to be the from connected everything to the intelligent everything environment system ecosystem we are trying to establish over there. So this is one of the platforms which have been motivating us to move from connecting to the intelligent systems, where the multiple technologies have converged during the recent times. To name a few, like in 5G advanced or 6G environment, what we are seeing. So we are seeing the NT and non-terrestrial networks being integrated, AR, VR being integrated, and IoT, industrial IoT being integrated, and we have been talking about the other technologies like digital twin being integrated, industry 4.0 to now presently the 5.0 also being coming into the picture of under the area of intelligent systems. So with this, like this has been like given a backbone through that of the AI/ML technology, or the what we can say the tool that has been working at the backbone of the whole networking system to enhance major performances of the 5G or 5G plus or 6G to a larger extent. So when we talk about intelligent and everything, intelligent everything is a 6G environment. So this is not just the, we are not going to just talk about the connectivity over there, but also the network can sense, learn, predict, and also act autonomously with the integration of AI/ML to the core. So this is the major thing why we call this as intelligent everything over there. So the prediction is somewhere around by 2030, the 6G environment will come into picture to every one of us. So this as such like has been motivating, and these are the key features that have been or the services which have been integrated over there. Some other things like holographic communication also comes into picture. We have been talking about autonomous driving as such. ADAS services we have been seeing in the ADAS 2 also being coming into the vehicles and all. These are all like few things which are being like are the points that makes us to move towards the 6G over there. And one of such are going to be that smart city environment, wherein V2X communication is one of the major applications where we try to connect the vehicle to everything and try to understand how this is going to be there over the period of time. So the networks are going to become what kind of a networks we are going to obtain. So when we look into that over here, so this is basically like what we can say we are going to have a networks which are which are basically the self adaptive Then what we can say, we are going to have something like energy efficient. Then we can say that they are going to be semantically intelligent over there. So such kind of networks are coming up. So this has been like one of the outlines of 6G technology as such. So these are the motivational points which have been like the major things. When we talk about the key enabling technologies for 6G, so these are the few things we have seen that beamforming, of course, like beamforming, beam scanning, and are there in the even in the 5G systems also. But what has happened over here in the 6G is that we are going to have an advanced feature of this, what we can call as the massive MIMO part and beam scanning part and all, which have been like one of the backbones of the 6G over there. So of course, like as I mentioned, the ultra massive MIMO is one of the other parts which have been there, where the talks are there about this particular technology with respect to the antenna and also the transmission part also. So the other one is the reconfigurable intelligent systems, which have been RIS, what we have been focusing upon in the 5G plus or 6G environments. Of course, the integration of AI/ML at a different levels. What I mean by different levels is that when we talk about the protocol stack, when we talk about the protocol stack of the 5G or 6G as such, of course, the 6G is may not completely defined. We can stick to 5G protocol stack, wherein we are going to have the layered architecture, the 5-layer, then we are going to have a MAC, then we are going to have the RLC, PDCP, and we are going to have a RRC and SDAP as per the user plane and the control plane structures. But initially what has happened was the AI/ML was there with only the 5-layer, but it has slowly moved to the other layers also, like the MAC, and also for the decision making at the RRC layer also. It has been trying to contribute to a larger extent the complete AI/ML technology. So of course, the millimeter wave and terahertz communication is one of the other technology aspects that have been talked about in the recent times. So then talking about some other thing like that is the edge cloud continuum, wherein the real-time distributed AI processing is going to happen. That is one part which is going to be there. And when we talk about this, I missed out this one part, is that when we talk about this terahertz communication, that is from somewhere around 100 gigahertz to 1 terahertz have been like projected, wherein the ultra broadband bandwidth or TBPS speeds for our short ranges have been discussed in the length and breadth. Whereas continuing with the AI native air interface, because we talked about the 5-layer and the protocol structure at the channel level, if we are going to talk about the air interface, then the waveform coding, scheduling, optimized, everything is going to be optimized by the AI over there. So other one major part is the quantum computing, which have been discussed over there, and quantum computing, communication, and securities we've been discussed at a certain level also for this 6G networks. So this is the other image which have been taken from the ITUR, wherein this is going to be typically the 6G use case, wherein we are going to see the few things we have already seen in the previous slide. One is the immersive communication, that is what is the holographic calls, extended reality, what we call as XR. Then the digital twins, I just mentioned about that, wherein the real-time mirroring is going to happen for the smart factory environment or the human organs we can take up for the healthcare application over there. Then we are going to have connected robots which are going to come up, that is, and also the autonomous system. So AMR is also playing a major role, indoor and outdoor propagation of the swarm drones or such, which are going to be aligning to the industry 4.0 or 4.0 plus or 5.0, whatever you want to call it at this moment. So another is the tactile internet, which is going to be a millisecond level feedback for the surgery or remote control operations. So this is one of the other tactile is going to be the major thing. Then the sustainable networks, wherein the major thing that is going to be focused is on the energy efficiency and the carbon neutrality over there, how to optimize that. So that has been the focus point as such. So so this is one of the 2 to 3 slides where we are trying to work or try to understand how these releases are there and what is that they are going to provide us through the releases, what all the releases are talking about. So I hope, like, any questions at this point on the releases? Any 1 or 2 questions I can take up?
Any questions from the participants?
I hope, like, almost everyone is familiar with the releases. What I'm talking about is the 3GPP releases. 3GPP, to brief it, is the standards, wherein we are going to get the standards from the 4G to 5G, 5G to 6G. That's the third generation partnership project. So we got the first release for 4G somewhere way back in 2008, if I'm not wrong. Then we have moved since then to present release, that is release 20 or 21 might be. I'm not following much now. So base release which I'm working on is release 16. I have been working on much on the release 16 part. So somewhere like we have been getting this 4G over there. 4G, then we were into the LTE advanced, then we were able to get LTE machine, then we were able to get the NB-IoT. I think this was a time when we were there in release 13 was that. Release 13 mostly talked about NB-IoT, and majorly was the contribution of the release 13 was there on this particular release. Then we moved on the first phase of 5G, and release 15 was the initial 5G that we got. So for this, you can just refer to 3gpp.org for the website for these releases, and over there we'll be able to obtain almost all the releases over there. So to talk further on these releases, like each of the releases, I'm just concentrating on the protocol stack. If I'm going to concentrate on the protocol stack, then we are going to have a 36 series for the 4G part and 38 series for the 5G part. So 38.211, 212, 213 and 214 talks about the 5-layer part, and the other thing like the 38.321 talks about the MAC layer, 322 RLC, 323 for the PDCP, and the other 331 for the RRC layer, and so on. So similarly, we have got specifications and also the releases, that is a TS, technical specifications, and also some are going to talk about the TR, that is a technical report. TS is the standard where we are getting some technical reports are also available at this particular website. You can just refer to that over there. So continuing with this, like we have been like moving from this release 15, that is the foundation of 5G NR over here. The main focus or is the first complete 5G NR specifications we got. We have been getting the features of EMBB, URLLC, massive machine type communication over there. The basic architecture we were able to obtain over there, and the numerologies we were able to obtain, that is the scalable numerology, which is the different this is the major difference that is going to be there with respect to that of the 4G, that is numerology 0, 1, 2, 3 and 4 were followed by the 5G standards, whereas the subcarrier spacing was 15 kilohertz, whereas now we are going to have 15 kilohertz, 30 kilohertz, then 60 kilohertz, then we are going to get 250 kilohertz, and recently the 240 kilohertz standard is also available. And the first change in the coding techniques, that the LDPC and polar codes were introduced. Very LDPC were basically for the data part, polar codes for the control message part was carried out. And initially the non-standalone and standalone deployments were also discussed in this particular release. So some use cases were also brought into picture, that is the consumer mobile broadband, smart IoT deployments, low latency industrial automation were there. But what as per my knowledge, majorly the services were evolving around the EMBB features itself. So this is under what we call as a 6 gigahertz frequency, FR1 frequency range that was there. So a very minimal discussion on the AI/ML role was there, wherein mostly the traditional algorithms were adopted. Only few adaptations of AI/ML was here and there were mentioned in the releases, not much even in the releases. So release 16, 17, which is the enhancement of 5G over there, were discussed. And then over here, basically the first V2X was V2X with side link. I'm talking about V2X side link. What I mentioned is we'll look into that. Basically, the PC5, what we call as a link establishment. There are two things: UU link and a PC5 link. This is the regular link, whereas a PC5 link is the side link enhancements that we are going to get. So then we had the industrial IoT URLLC over there. Then the NRU unlicensed spectrum we were able to get over there, such that over here, like what we can say is licensed and unlicensed spectrum, how we can operate. Then the integrated block call was also there. They mentioned about the reduced capacity devices, what we call as the RedCap, and earlier the convergence of the NTN technology with the 5G was also discussed in release 17. So this is the first time, like non-terrestrial networks, how we can integrate those things were also discussed in this. So the use cases that were aligned over there was the smart factories, automated guided vehicles, automotive safeties, that is V2X, basically catering, and private enterprises, and the broader IoT and ecosystems were also there. So over here, to some extent, the earlier exploration of the AI/ML was put forth basically for the operations and management of the network automation as such. So this went on, and somewhere like we are here, that is start of 5G advanced technology and 5G advanced phase was discussed. So this is the timeline wherein we were trying to move deeper into the technology and make the network more intelligent over here. That is where like AI native RAN was discussed, wherein the resource allocation, beamforming, for that we were able to do that, and intelligent edge computing came into picture. Advanced NTN technology was also there, and we were also talking about the concepts such as digital twin and all was also included. So these are the few use cases that have been listed. That is global broadband via satellite, holographic calls, and metaverse apps, and all such as smart grids, energy efficient smart grids were also discussed in the as a use case over there. So this AI has moved from supporting role to the core role over here. This is the scenario at present, wherein the AI native RAN has been one of the key features, where AI is going to be embedded directly into the scheduling, channel estimation, and self-optimizing functions. So this is where for example, like we can think about the channel estimation as one of the example. We were using some channel estimation technique like MMSE and all, or Kalman filter as such, wherein we need to hear to the channel every time continuously and then try to respond over there. And this is the time where the decisions are going to be made at the what we can say that the MAC scheduler, that is the advanced MCS technology came into picture. That is a modulation encoding schemes were there. So this is like one of the things which has given us the understanding of the whole technology, how it has moved further. So just a second. So the next is like the pre 6G era we are where presently. So this is the time where we are trying to understand how we can utilize AI to the best part, and trying to bring it into the network. And as I mentioned over here, from the supporting role to the core role, we are trying to move forward. So this is where we are trying to make it more semantic, deterministic, and AI native network over there. And this has like helped us to move from the spectrum crunch, what we can call it as, to the terahertz level. So this is one of the main thing that is there. So another key point that we can mention over here is the demand for the deterministic latency. That is what we have been calling in the URLLC. That is, we are trying to improve the latency over there, but it was not possible to that extent. But AIML will help us positively to make the latency very minimal. And what we can say, the deterministic latency might be lesser than 1 millisecond, what we have been thinking about in the ultra reliable low latency communication as such. So talking about the beyond connectivity thing, where we're trying to integrate the communication, sensing, and computing together. So this is the period where we can bring or converge a multiple technologies to one thing and make it more hybrid over there, such that the 6G hybrid can be thought about, wherein with that of Wi-Fi, NTN, optical, quantum, those things being integrated or converged to one technology or one umbrella of 5G beyond or 6G as such. So basically, this is the one of the architectures. This slide that talks more on that, wherein they're going to talk about the side link as one of the major understanding. So this is the architecture for the V2X architecture. As I mentioned earlier, that majorly I'm working on this particular release, that is release 16. This has been taken from release 16 as such, wherein we are going to see majorly the PC5 side link and also the UU interface over there. So basically, the what we started with, when we talk about the V2X as such, like we had multiple options for V2X. One, we can say through some other networks which are terrestrial networks which are other than 4G, 5G and all, like DSRC and all are the networks. So other than that, we started with the LTE over there. LTE V2X was one of the earlier specifications for the V2X, which was specified in release 14 and also some part in release 15. So this was going to introduce a basics of side link, what we call as side link, or the PC5 connection as such. So the communication for the vehicle. So this is going to be mostly the broadcast messages for the safety. Example for this, we can say that BSM or the CAM messages were there for our this thing. So the major leap, what has happened is in release 16, there was a major leap wherein it is going to start supporting the advanced V2X services, like what we can say the platooning service, vehicle platooning was one of the services, or advanced driving, extended sensor sharing, or remote driving. So these were the few applications, what we can say, that were supported by the release 16 as such. So next was the NR V2X introduced a flexibility, higher throughput and lower latency, and also the new side link features. Over here, what we are seeing is the interface, that is a two interface, UU interface, and the PC5 interface. So UU interface is what? UU interface is nothing but a traditional interface, traditional communication interface, which is going to be via the base station or the GNB node to the GNB core, sorry, the 5G core. So this is the interface which is going to do that. So this is basically used for the non-real-time V2X part or the cloud updates and traffic management. So this is going to provide a global connectivity and also the network control over there. So when it comes to PC5 as such, it's a direct communication network which is going to connect the V2X. What I mentioned by V2X is the V2V, which is a vehicle to vehicle. V2I is the vehicle to infrastructure. V2P is the vehicle to pedestrian links without the over here without any GNB involvement. You are observing that the GNB is not involved over here. The two vehicles are going to be interfaced with the help of the PC5 over here, and we are going to have these services being provided. So this is going to we are going to get what out of this, the PC5 interface. Basically, this is going to enable the low latency. This is going to enable the low latency, high reliability. The reliability is higher. Then we are going to also get the services or the support like what I mentioned over here. If you remember, it was a broadcast kind of a service. Over here, what has happened with the PC5 is that we are able to obtain something as a, what do we call as a unicast, groupcast, and broadcast transmission. All three we will be able to obtain. So what we can also say over here, one point what I can mention over here is the operating mode, like mode 1 and mode 2 are going to be the operating modes, wherein this is going to be the mode 1. What we can say is going to be scheduled by the GNB over here, whereas mode 2 is what? Mode 2 is the autonomous resource selection by vehicles. So this is one thing. Then coming to the core part, that is a 5G core network. So we are going to have a PCF. PCF is the policy control function, which is going to apply the policy for the V2X flow. Then we are going to have AMF, SMF, and UPF. So these are the standard 5GC functions to manage the access, session management function, and the user plane traffic over there through UPF. So then we are going to have a NWDAF, that is basically the network data analytics function, which is going to collect the data to optimize mobility and the resources over there. Then over here, the application server is going to sit in through the N6 interface, that of the UPF, and this is going to operate when we are going to have a UU interface in between. So continuing with this, like to talk a few points on release 16 as such. So this is going to be providing us a flexible QoS service, wherein the different services like platooning versus infotainment can have a different QoS profiles over there. The new side link features like unicast, multicast, whatever been mentioned, that is going to be the beyond that of the 4G V2X, that is the broadcast system. Then we have got a new thing over here, because you at a MAC as well as file layer, the HARP function, that is a HARP feedback on PC5. This has been really one of the key things which has given a improvement over the reliability compared to that of the UU based interface when you compare. So then we are going to have a relay support, that is, the vehicles can act as a relay to extend the coverage. Suppose we are going to have another vehicle, so one vehicle can act as a relay and extend the support to the another vehicle over there. So then the integration with NR numerology, as I already mentioned, the numerology is going to be 0, 1, 2, 3, and 4 over there, which is going to give us the subcarrier spacing. So this is a scalable subcarrier spacing compared to that of the LTE. Over here, this has provided a scalable for the different mobility latency requirement as per the application, the integration of NR numerology we are going to take up. So then with some cooperative driving, we will be able to obtain the positioning accuracy and also the improvement we are going to observe over there. Then the security enhancements like better authentication and integrity for the safety messages is also been looked over in this particular release and also the architecture. So what we can achieve with this, other than this kind of a setup that we can do for a testbed development, other than that, we can also work on the hybrid operations, wherein a vehicle may use a PC5 for the real-time safety and also UU for the cloud-based service simultaneously. So to wrap up this particular architecture, what we can say is that it is going to bridge the gap from the LTE V2X, which was a basic thing, and making it more intelligent at a certain level. Then also, as we have moved along, we are going to obtain a cooperative perception V2X with the more service categories. I have one slide on this which talks majorly on this. And also it is going to provide the foundation for basically AI/ML integration, which we have seen later in release 17, 18, this integration over there, where the intelligent RAN, that's what we call as the RIC over there, intelligent RAN controller, RIC, can be optimized with the V2X, wherein we can say that non-RT and RT parts, XApp and RApps are going to be utilized over there. So that is totally a different level of concept at this particular moment of time. So this is going to also prepare for the 6G V2X, wherein we can talk about the semantic communication, deterministic latency and all. So this is how, like, this architecture, this is going to be one of the base architectures from where we can build the complete V2X platform if we are working on the V2X system as such. So this is where what we can say how AI/ML has transformed 5G architecture into the intelligent one and making it more adaptive network through the RIC, SMO, and a distributed intelligence as such. So basically, like while we were discussing in the previous slide, the release 16 gave us the architecture. AI and ML are what make the V2X truly intelligent. Here, like, we are going to have the two important concepts, what we can say. One is the RIC, that is a radio intelligent controller, and one more is the SMO, that is the service management and orchestration over here. The RIC is what? RIC is basically allow us to deploy the apps, that is what we call, what I just mentioned was the XApp for near real-time functions, and RApps for the non-real-time functions. So these are what, in one word, what we can say, that is, these are like something as a plugins that optimize the radio network using AI. So the next one that we discussed, like one more very key important concept, that is SMO, that is the service and management orchestration. So this SMO like orchestrates the service across the network, ensuring a smooth end-to-end optimization. So So we might like think about where does this AI ML come into picture over here. This can be one of the questions. Like with AI ML, like what we can do over here is we can predict the conjunction. We can predict this conjunction and then perform the proactive handover, perform some proactive handovers. Then we will be able to do some dynamic allocation of spectrum. Then also we will be able to mitigate the interference to some level. So what we can say with this, like how this is can help us. Suppose you can think of one scenario wherein the system is going to predict heavy traffic at a junction. So in that, like it can pre-allocate more radio resources to a particular area, ensuring that vehicles do not experience any kind of a delay in safety critical message exchange. I just mentioned about 2 messages over there. Like that, we are going to have 13 different IEEE standard messages which are going to be exchanged between the 2 vehicles. That is BSM CAM is one of the examples that I just mentioned over there. Then what we can say is like it is going to perform the entire V2X communication model into a predictive adaptive system as such. So coming to the the main thing, why, like how this has been integrated, AI, ML, and 5G. This has been taken from this particular references. These 2 are the references from which I have borrowed this. So there are 4 major things that is going to happen, or the 4 major applications what we can bottom up or bottom line over there. One is the resource. Sorry. First one is the resource allocation. The second one is the mobility management. Third one is the quality of service and experience prediction. Sorry for that. And experience prediction. And the last one, fourth one is what? Fourth one is the fault detection and self-healing. So the first one, if you take up the resource allocation as such, like AI is going to model dynamically allocate the spectrum and the power to maximize the efficiency. So unlike the static scheduling, AI is going to learn the pattern and going to adapt in the real time. So this is how the resource is going to be allocated using AI over there. Then the traditional handover, wherein we move from one cell to other cell, like and are going to be a rule based, and often they are going to fail with the vehicles which are moving very fast. And with AI, what we can do is we can predict the mobility pattern, and also like we can trigger the handover before the signal is going to degrade over there. Sorry. So the next one is the quality of service and also the experience prediction. The AI will help us in predicting the quality of service, and also it is going to understand how the behavior of the users and also adjust the pattern parameters proactively. And also it is going to ensure, suppose we are using something on the video calls or then something, like we are going to get a stabilized video calls or streaming over there, or we are doing some gaming services or we are operating the gamings and all, there is going to be less fluctuations such that the QoS, the quality of service is going to be maintained and the experience is going to be bettered over there. The last one or the last applications, what we can say is that the fault detection over there, the fault detection and self-healing. When we talk about this as a AI/ML integration, so the network is going to generate the massive amount of telemetry, and AI can detect some anomalies what are going to be there. What we can say, the anomalies are going to be something like a sudden drop in the throughput in the cell, or it's going to trigger the healing action. So this is like these are the four major things where we can see the AI/ML is going to be directly involved with the 5G, making it more experiential, and also we are going to get a better quality of service over there. This is about the complete basic foundation where the AI/ML is going to be integrated either in 5G or in the next generation 6G as such. So, so when we talk about these things, like two major collectively, I told about 38.817 is going to talk about the functional framework of RAN intelligence, and this 28.908 AI/ML framework is going to be giving us the workflow for the 5Gs over here. So these are like the standardized for the AI/ML in telecom for extremely going to be an important reports, technical reports, which are going to address this integration of AI/ML as such. So, so this 38.817, what we are talking over here is going to define the functional framework of the RAN intelligence. Therein, the RIC is the central concept, and it is going to define it is going to basically define how the AI is going to be modeled, and it is going to interact with the radio access with the radio access, and then how the data is going to flow over there as per the requirement, and also how the decisions are going to be carried out based on this. So those who are working with the AI/ML when 5G, this is going to be really the framework where they can start thinking, and it can help us in developing. So this is the workflow. The next one, 28.908, talks about the workflow over there, and which is going to describe the AI/ML steps over there, how the data is acquired, and then collecting and measurement from the network elements, then the pre-processing, then cleaning, the filtering, transforming the data into usable format over there. Then we are going to train and deploy, that is building the AI/ML models and deploying them into the network. And finally, the AI/ML interface, that is running the models in the real time, to generate the insights and to control the actions over there. So one point, just this is at the top level, like we have like different vendors wherein they might be working with AI/ML models over there. So this is like this why the standardization, where the standardization will help is like basically for interoperability, this standardization workflow will help us, wherein each of the AI/ML models which have been developed by different vendors can work together in one network such that it will be avoiding the fragmentation over there. So this is the reason why this kind of a framework has been given to us, wherein this is going to be the base part. So moving on, this is at the top level understanding of the one of the projects presently I'm involved with working. How this V2V we are trying to work on. So basically, like one of the most exciting applications what I can mention at this point in V2X is the cooperative perception, where in the cooperative perception part, we are going to have the data acquisition and processing, message transmission and sharing, and cooperative decision making part. And this is going to be integrated with the 5G environment, where we are going to see some layered architecture over here, the device layer or the physical layer, what we can call the network layer, and then the cloud computing part, and therein real-time data processing, app hosting, interoperability and scalability, data storage and management, MEC, then the security part are going to be there in the cloud computing part, and finally the application comes and sit over there. Like if you want to break this into certain stages, what we can say is the vehicles and infrastructure nodes like roadside units or even drones collect the data using the sensors such as cameras, lidars, radars, and so on. And the second is that the data is going to be fused and going to be processed locally, often which we can say that compressed to a reduced redundancy over there. Then the next point is that the processed perception data is going to be shared among the vehicles. This and also the infrastructure nodes through the low latency V2X links that we are going to obtain. So finally, what we can say is that the cooperative decisions, for example, deciding whether to brake, change the lane, or adjust the speed, such kind of an decisions, it will help. The cooperative perception based V2X will help in these kinds of things. So this approach enables more safety applications like collision avoidance, elimination of the blind spots, and also the smooth flowing of the traffic. This is also like helping in these kinds of applications. So it depends upon how the data is going to be fed, either through camera, lidar, and all. We have been seeing like these are the few devices which are going to be there on the vehicle at the moment. So this is how this has application or the complete project is presently working on. So so this is another example wherein we are trying to bring in the AI-driven V2X communication with 5G new radio sidelink integration. The sidelink integration, already we have mentioned that it is going to be the PC5 integration that is going to be there. So this is the high-level architecture of that, wherein we are trying to bring in the concepts of the RAN part, that is the ORAN part over here, and also the XApp and RAP that we just mentioned about a slide or two slides back, wherein we talked about RIC and also the SMO over here. So we are trying to engage the communication with the help of this particular concept of RIC and SMO over here. So these are the applications that can be developed with this, that the same what we discussed, the collision avoidance, platooning coordination, adaptive traffic signal control over there. So we have discussed the rather than this, it is going to be 16 actually. This is actually the 16 release 16. Sorry for that, release 16. So how this is like V2X, one application we just looked in, that is V2X as application, which was there in LTE V2X, how it has transformed in 5G V2X. Then how this same V2X has evolved. For example, one application of V2X, for example, what we have taken is the platooning we can take, or the cooperative driving support we can think of. So how this will evolve with the help of AI/ML. So the AI/ML basically, like we started applying since release 17, 18, 19 probably. So when the 5G advanced, we started with. So this AI ML concept, when it has been enabled for the same V2X, what would be better? Like we spoke about the handover over there, so we can think about the AI enabled predictive handovers. So this is one AI/ML based predictive handovers, which will help us the handover before the degradation of the signal. So from when we are moving from one cell to the other cell at a very fast pace. Then we can also think about the QoS slicing. So slicing, we have been discussing about the slicing is one of the key things since the advent of this particular 5G technology as such. It might be the slicing with respect to the network slicing over there, or now we are talking about the QoS, quality of service slicing also. So then the extended side link capabilities, the PC5 capabilities I'm talking about, this is where the predictive intelligence first enters into the picture, and we will be able to get some advanced kind of a features over there in this particular thing. As we move on to release 20, what might we might get? So if we are going to move into 6G or release 20, we might get into something what we were discussing as the semantic communication as such. Becomes, this is going to be like one of the reality in the next few years to come, and then we are going to also obtain a networks guarantee, deterministic latency, and the AI native orchestration is going to be inbuilt over here. So this is what we might get in the near future of this particular part, what we can say. Well, coming to what are the real challenges and also the industry context as such, if you want to look in, one of the challenges is the handling the ultra low latency and reliability. We have been seeing this so we are talking about the V2X as application. So especially when it comes to the applications such as under V2X, the vehicle platooning. So this is going to require a deterministic end-to-end latency, which is going to be targeted as less than 1 millisecond in 6G. So this is like the currently that what we can say, it is somewhere around falling somewhere around 10 milliseconds, which is not enough for the system. So even the 10 millisecond delay at a what we can think is when we are driving at 100 kilometers per hour can cause serious issues. So this has to be understood, and AI/ML driven predictive resource allocation can help us in this, wherein we can anticipate a congestion and reduced latency over there. So this is where the AI/ML can bring in. So next is the mobility and handover. We have been seeing this as one of the challenges. So we can take up the same speed if at all 100 to 120 kilohertz, sorry, 100 to 120 kilometers per hour, which is going to cross the cell boundaries at a faster rate. So handover failures we cannot afford. So, and also the packet loss we cannot afford. So this rather than this traditional handover, which are very slow, causing this packet loss and service interruption, what we can say, AI-based mobility prediction can help us in this in forecasting the vehicle parts and also preparing the handover in advanced and in pretty advanced timeline. So the next one is the scalability in a dense environment. This is the issue, what we can say, what we are trying to cater to the MMTC under MMTC applications kind of a thing, wherein this can be the issues at junctions, intersections, wherein we will be observing some traffic jams over there and may cause the communication lapse. So this is going to be create a side link, what we have been talking about, a PC5 as a side link congestion issue. So this can be addressed over here through the semantic communication, which we were talking previously, wherein we will be able to send a raw sensor data, vehicles exchange, and compressed meanings of this. So this is how this is going to be helping us. So next issue that we can see is the spectrum fragmentation, wherein V2X must operate in some licensed spectrum under 6 gigahertz, that is the 5.9 gigahertz, we can say, and unlicensed band like NRU band, and wherein they are going to coexist. We saw few unlicensed band like which are going to cater the same applications of this V2X over here through DSRC. So this is going to create a interference and going to also create some complexity with the regulatory issues. So AI-driven spectrum sensing and dynamic allocations are needed to solve this. Like one of the things, like we can bring in the energy detection spectrum sensing is one of the techniques. Very primary technique is this, which is being adopted in few applications. We can make it more dynamically adaptive and make this sense the frequency ranges which are being transmitted. So next is the trust and the security issues, which we can say that we can send some fake emergency braking messages to the platoon of the vehicles. Then this can cause some consequences that can be very unhandleable, and this, like, we need to robust the things and to detect the AI powered detection techniques, such that we'll be able to do some federated learning for the intrusion detection and the blockchain to ensure the message integrity over there. So this can be like the targeted few points that can be there for this. So next is the energy efficiency. So the autonomous vehicles and connected cars constantly sense, process, and transmit the data. So this drains the batteries, especially in the electric vehicles. So this issue can be handled. That is the energy aware scheduling. Green AI models can be deployed, and also the offload computations to the edge servers, which are being done to certain levels. Wherein presently, if you observe the whole structure of the protocol stack, where we have divided the file layer also into two levels. That is the one interacting with the RF front end part, what we call as the low-fi, and the other part is the hi-fi. And above this, MAC layer and other layers have been disintegrated, and this is going to be there at the software level at the cloud platform. So this has been already achieved, and also the plans are there. Like few people might be discussing on this, like hi-fi also being on the cloud platform, and only the low-fi being attached to the RF front end part. So this offloading computation to the edge servers, cloud services have been one of the points to discuss, which will help us in reducing the onboard power consumption to a greater extent. So these points, like the spectrum fragmentation, security, and energy, are not a kind of a side challenges. They are the kind of what we can say, they are the main part of the V2X challenge issues, and such as to make it more safe, reliable, and sustainable. So these points needs to be understood, and we need to address those issues. When we talk about the industry context of this, in the automotive sector, OEMs like Tesla, Toyota, BMW, and other companies are investing very much on the cooperative perception and platooning, with a strong push on the AI-powered ADAS technique, wherein they must comply to this ISO 26262 standards as such. Then talking about the telecommunication parts, like the Verizon Telecom are going to test the AI-driven RANs, and they are going to have intent-based networking, wherein the vendors like Ericsson working on the network slicing to guarantee the URLLC for V2X, while Nokia is also exploring on the semantic communication as such. So So talking about the edge and the cloud ecosystem, which are going to be the major providers, you already know that AWS, Azure are the major providers, are the critical for the hosting the low latency vehicular services, vehicular services over there. And these platforms, like what we can say, the NVIDIA, are being used to train the large-scale machine learning models for the autonomous driving systems. So, of course, other than this, we have been seeing some uh, standard regulations from 3GPP, wherein how this AI ML is going to be enabled and integrated. We have got the frameworks and the workflows for that. We saw that recently in one of the slides. We have got some inputs from the ETSI, which is going to ensure the coexistence between the different V2X technologies. We are going to have the regulatory bodies, organizations of like the SEC and EU are focused on allocating the necessary spectrum for V2X. So this is what we are foreseeing in the next coming years. What we can say that by 2025 to 2030, we can expect the transition from 5G advanced to early 6G trials. Research test beds are already being deployed to some levels across the world. So post 2030, we might see some commercial rollouts of 6G also. By then, the network will also provide some deterministic latency communication and fully AI native orchestration to some level. So the impact is going to go beyond this automotive part to healthcare and to other applications. Like 6G might be used to enable some remote surgeries with the real-time tactile feedback. It might be used in the smart cities, wherein the digital twins might be able to manage the infrastructure. Industry regulations and industry 4.0, 5.0 adaptations might give us or pave us the way for the predictive manufacturing with the minimized downtime. So overall, we can say from this understanding, wherein 5G was giving us the connected everything, the 6G might deliver the intelligent everything system as such. So what we can say is to some level, this has helped us in understanding the whole scenario and trying to give us the connected everything to intelligent everything understanding to us. So two hands-on experiments are just very small. This is not, I'm not going to take anything on the what we can say, the real-time data set, some generated data set we are going to work upon and trying to understand how this is all about. So to just dive into that, hope you are seeing my screen at this moment. There are two hands-on exercises that have been we'll be discussing in the next few minutes. So the one is that AI-based V2V message prediction. This is what we are trying to do is using the supervised learning. The objective over here is to predict the next state traffic conditions or the vehicle position in a small V2X network using the regression technique. So wherein we'll be able to do some understanding with the telemetry vehicular data, historic data. But over here, the synthetic data I have chosen because it was taking a lot of time to do the iteration and to converge the results in the given time slot. So because of that, it took some time. So because of that, I went for the synthetic data over here. So the next application was what was thought about was the AI-based platoon speed control. This is a reinforcement learning technique, wherein we are trying to demonstrate how the AI/ML can optimize the speed of the vehicle platoon to maintain the safe distance between the two vehicles, and also it is going to reduce the fuel consumption as such. We are trying to use a MATLAB toolbox over here such that to train the platoon control, and we are going to observe the speed of the vehicle and how much distance they are away from each other. So the agent is going to decide on the how much to accelerate or decelerate on the vehicle. So I'm not getting into the real mathematical part, wherein like few things what have been over here is that so when you look into the approach of this particular problem, that is the first problem, this is what is the learning map from the features of the labels, that is a regression approach, wherein we are going to predict the position and also the telemetry traces we are going to obtain over there. Wherein the second problem that we are going to handle is for the to learn the policy from the interaction and rewards. We are applying the reinforcement learning over here, wherein this is one of the kind of a feedback techniques, as you already understand to some level. This technique, the reinforcement technique, wherein when we talk about it is going to apply some equations like as this one was applying the regression equation over here. This is the Bellman equation and also the reward shaping equations we are going to apply and going to obtain some safe and effective platoon behavior over here in the second part. And what we can say in simple words is this is the application wherein we are going to simulate two vehicles. One is the leader vehicle and another one is the follower vehicle. So that is the application that we are trying to bring out to you people. So any questions at this point of time before we move into this?
Any queries from the participants?
So the synthetic data has been chosen over here, and as already mentioned, like regression technique has been adopted, like kinematic state transition physics has been trying to understand, wherein position at the time we are going to calculate and with what velocity and acceleration it is going to move, and the sampling interval we are going to do that. So a baseline linear regression algorithm we are trying to implement and then put it onto the neural network regression, what we call it as the function of xt. Xt is what? Xt is our position at a particular specific time intervals. So with that, we are going to obtain some trajectory position of the vehicle, wherein the true line is going to be mentioned with this blue line and the red line gives us the linear regression, and the neural network, as mentioned, f theta of xt, that is the network weight that is going to be learned by the gradient descendant algorithm, is going to be put forth. And finally, the mean square error is also calculated over here. I think there might be some issue. It's giving 0. Okay, fine. So wherein the there is some difference, but still it is giving 0 over there. Some predicted position and the number of samples it is taking over there. And also, in short, what we can say that it is going to obtain or give us the neural network MSE value, which is coming something like this. So this is the example wherein we are going to obtain this particular results. So this code has been generated using the synthetic vehicle data, wherein we can also obtain the data through this particular website, wherein this is the highway data set from the NG sim. So this can be replaced with this data set. We can replace that if we download the CSV file, and we can do this particular trial. We can do this, and this is going to further train the model with the regression model, and then we'll be able to predict the positions of the vehicles, so that we'll be able to evaluate the accuracy using the MSC over there. So moving on to the next. So as I mentioned, like we are going to have one leader vehicle and another one is the follower vehicle, wherein we are trying to apply the Q-learning, one of the standard learning algorithms of the reinforcement learning technique. Over here also, we are trying to use the synthetic data and trying to obtain this particular condition. The kinematics over here is, like as I mentioned, one leader and the follower vehicle, wherein the state variables are going to be understood, and we are going to over here, like the reward functions that is going to be encouraged over here, such that we'll be able to obtain a smooth following system of the vehicle to vehicle communication. So as I mentioned, the Bellman equation of the Q-learning update we are going to get, wherein the agent is going to learn the long-term optimal policy by the adapting the Q values. So if you go back over here, one of the basic thing that is the agent is going to learn this particular thing, that is a Q-learning algorithm is being provided. So action is going to be selected with the probability of random actions to that of the argumented values are going to be carried out. So this particular code is going to define or set up a platooning equation, wherein we are going to obtain some results through this, the sinusoidal kind of a flow graph we are going to obtain, wherein the speed and the speed of the leader vehicle and the following vehicle or the agent vehicle, what we can say, we are going to obtain, and we are going to also see what is the amount of the gap that is going to be there. So it is going to be obtained by the state such as gap, or with respect of the respect to that of the relative speed. So this is what is going to happen with the reward function that is going to be there. Then it is going to use the Q-learning function, which is going to be continuously update the table based on the rewards that is going to get. And we are going to obtain the training loops from multiple episodes over there, and we are going to get the following vehicle, how it is going to improve over there. So this is how, like every training or every iteration will be able to obtain a better results through this particular kind of a AI/ML integration over there, such that the vehicle can maintain a safer distance and also the smooth driving conditions as such. Suppose like one point before conclusion, I just wanted to tell we have got something as NG sim, wherein we'll be able to get the data set for the highway trajectory data set. Then we have got high D data set. What is I will share with you people over there. This is from the Germany, wherein we'll be getting the trajectory collected via drones. So this is the data set from that. And the dense urban complex maneuvers are the other one, wherein we will be able to apply the RL part scenarios over there. And also we have got something what we call as Argoverse, which is going to be one of the data sets wherein we are trying to understand the lane graphs urban driving trajectories and all, good for especially the predictive models, what we are going to obtain. Then we are going to have something as level 5 new sensors, that is the sensor rich data set wherein camera, lidar for perception trajectory extractions, which are going to be one of the best one. So these are the few data sets what we can have. So with this, what we can say that will help us in better integration of V2X 5G system for a multiple applications, and try to do some initial POC level implementation as such. So to conclude this particular session, like few things that we have been trying to understand how this evolution of 5G to 6G has helped us in connectivity to intelligence. That is, 5G establishes the connected everything to 6G to intelligent everything through the AI ML native networks, and ML as a core enabler. How this has enabled, like this has been a this has been working at the back end to a certain level. Now at a core level, it has been brought in, wherein multiple scenarios, basically like 4 levels, where we saw that how we can bring in AI ML at an initial level for a 5G system as such. So this is how we can integrate at the UV side, RAN side, or the edge part, or at the cloud level. So wherein overall this is going to give us the improvement in the latency, reliability, efficiency, and also the scalability for the critical applications like V2X. So the next one is that the how it has impacted and how this is going to provide a better environment to us as it evolves into 5G plus to 6G completely, like multiple applications on healthcare, manufacturing, or urban infrastructure have been thought about. How this is being brought in, as the complete 6G network is a kind of an umbrella system for every one of us, wherein multiple technologies are going to be integrated and converging to a greater extent. So by 2030, we might have a 6G, that is system being deployed to a greater level in multiple cities, and major chunk what we are seeing at present, that is the latency issues, wherein we are not completely able to work on URLLC based applications or on the MMTC application as such, wherein we are basically concentrating on a EMBB part. This might be like bottom line, and we might get a better system which will operate under 1 millisecond of latency. So with this, I would like to thank all of you for listening to me for last 1.5 hours. Thank you, everyone. Thank you, MIT and the organizing team, Mohit sir, for providing me the opportunity.
Thank you, sir, for your enlightening session. Any queries from the participants? Any queries? So is there any designing fabrication facilities at your region, means for 6G?
Fabrication, sir, sorry, I missed out.
Antenna fabrication at your region means?
We have an anoic chamber and RF this thing at our institute. We have that. We have the facility over there, the complete anoic chamber, and the RF facility is available. I am not part of that actually.
Okay, sir. Okay, sir.
I'm not the right person to answer that, but we have that.
Okay, sir.
We have till 6 gigahertz facility, but I have been predominantly working on the 5-layer part on the signal processing. CI/CD is my basic thing, and algorithm development is my core work, because I've been like doing that with the previous organizations like Sasken Technology, where I was part of MediaTek and Altiostar. So basically, the protocol stack development on L1 and L3 were my interest.
Okay, sir. Thank you, sir. Can you share the PPTs for the
Yes, sir.
participants?
Yes,
Okay,
sir.
thank you, sir.
And if at all you want to get in touch with me for any reason, like I'm just sharing this few slides I need to remove. I will the 1 or 2 slides where the architecture is being defined.
No problem.
Uh,
No problem.
so you can just so I shared in my chat the details over there,
Thank
my
you, sir.
number as well as this thing.
Thank you, sir.
Yes.
So, on the behalf of the participants, organizing committee, and MIT group of institutes, I extend my gratitude to Dr. Ramakrishna sir for delivering such a wonderful session. Sir has nicely explained in detail about 5G, 6G, about the different release, AI, ML in 5G, 6G. Hands-on examples are really very good, sir. Thank you once again for sparing your valuable time and deliver a wonderful session, sir.
So
Namaskar and good night, sir.
just
Good night to
one
all.
point I just wanted to add,
Yes,
like
sir.
suppose if you are interested in developing the stack level development, the protocol stack, wherein you can use at a lower price, we have some boards like Lime SDR and all, which are operating under 3.5 gigahertz.
Okay, sir.
So rather than using the higher end USRP boards SDRs, that is costing us somewhere around 2.75 lakhs, wherein that is very costly over there. So because I have like recently purchased 8 SDRs of this 3.5 gigahertz, previously I had some 4 SDRs on NI from NI, which are operating above 6 gigahertz till 6 gigahertz frequency ranges. 2954, one of the advanced SDRs, and one more is B210 and B220. We have been working. I have integrated the hybrid testbed, which is working with the open air interface for this. Integrating the SDRs, these B210 with the open air interface, and the other SDR, like low cost SDR, are working on the hybrid platform that is using the Python. So that integration you can make, and that will be a feasible setup for people who are working on transreception of data as such.
Thank you, sir. Thank you for the information.
Thank you.
Thank you, sir.
Thank you, everyone. Good night.
Good night, sir. Participants can fill the feedback form. Participants can fill the feedback form and leave the meeting. Thank you all. We will share the PPTs and recording after consulting the speakers.